how do we reach that? By working together. So the theme of the Swedish pavilion is also co-creation for innovation, and that's what we're trying to organize here together with all of you. So this morning we touched upon new paradigms to research and innovation. We need to invent also how we innovate, embrace new collaborations, partnerships, so that we can prepare our society for today, but also tomorrow's healthcare. And we also went into the importance actually of the prevention and early detection of cancer as the main driver for eliminating by detecting earlier. We will now move into our third theme, which is the digital transformation and the global uptake of personalized healthcare in cancer. So precision medicine, as many of us say, or personalized medicine, as others call it. But moving then into this topic. So first I would like to welcome one of our distinguished colleagues from Sweden, from the Karolinska University Hospital and Karolinska Institutet, Professor Dr. Richard Rosenqvist Brandell, Professor in Clinical Genetics, who will give us the road towards personalization of cancer care. So welcome, Richard. The scene is yours.
Thank you very much, Ebba, and thanks to the organizers for inviting me. And also, I'm really delighted to present our experience from implementing personalized medicine at national level. So, do you see my slides? Yes, you do. You have probably seen this in different versions. But I just wanted to underscore that precision medicine or precision health is really a game changer, and this leads to transformation of healthcare, or as someone says, a modernization of healthcare. And to underscore this, as you heard probably yesterday by Jenny Nordborg, in the Swedish life science strategy published 2 years ago, it is stated very clearly already in the summary that they want Sweden to be international leader in the implementation of precision medicine. So, of course, we doctors in healthcare, including myself, always wanted to give the right treatment to the right patient. But what has happened is that we have got new technologies that really can help us to characterize the unique profiles of individuals. And for me as a clinical geneticist, it has been extremely exciting with this new toolbox that enable us not only to do research, but to move these technologies into diagnostics. Today, we can do clinical whole genome sequencing, but also, as you will see in cancer diagnostics, to fish out the genes that are of most interest. We call that gene panels. So how did it start in Sweden? We have a national infrastructure for research called Science for Life Laboratory. And when they started to implement the new sequencing technologies, we contacted them and said, shouldn't we try to move these technologies into healthcare? And thanks to this collaboration, we started the clinical genomics platform, which optimized and adapt these new technologies for diagnostics. And when forming this, we started to discuss, shouldn't we do a national precision medicine or genomic medicine initiative? And that is how we contacted all universities and university hospitals in Sweden and said, are you interested? And fortunately, everyone was interested and wanted to be on board. And I think this discussion about co-creation, it has really been clear from the start that everyone in Sweden really wants to do this together. It's not only healthcare and academia, but also patients and industry are included, because we really need this in order to implement precision medicine at a national level. So this project is funded by the government through Vinnova, and now we have got a longer funding for until 2024, which we are very happy for. So this was really a bottom-up initiative that we saw the potential in working together. We have established 7 genomic medicine centers at the university hospitals in Sweden, and we have a sort of a virtual infrastructure, but the genomic medicine centers are real infrastructure where the precision diagnostics is carried out, and also they are building up teams to of course deliver this to patients and guide patients and give treatments, etc. And we think this is a good way of harmonizing at the national level, providing standards, guidelines, and also, since, as you probably know, Sweden has very good biobanks and registers, so we think this will add an important part with population-based genomics data. And our primary goal is really that all patients in Sweden, independent where they live, should have access to precision medicine. And besides the regional hubs, the genomic medicine centers, we have established a national genomic platform in the west part of the country to share the data, genomics data. Currently, we can only do that within research projects where we have ethical approvals, since secondary use of health data is not allowed so far in Sweden. But we see in other countries like Finland and Denmark, they have changed the legislation in order to enable that. But this national genomic platform is very important for us in order to within healthcare, to improve diagnostics, for research, but also for innovation. So these are our focus areas, from rare diseases to cancer to infectious diseases, pharmacoeconomics, and complex diseases. And we have a number of working groups. Of course, informatics and data sharing is extremely important, ethical, legal, communication, and education. We have dedicated efforts working with patient organizations in order to leverage the knowledge about precision medicine, health economy, and of course industry collaboration. And I will give you some examples that precision medicine is here. In 2015, we started to do clinical whole genome sequencing at Karolinska, and my colleagues have summarized the first 3,200 patients that received clinical whole genome sequencing, and 40% of patients that were previously undiagnosed got a diagnosis, a molecular diagnosis with whole genome sequencing, showing the power of clinical whole genome sequencing. And this is a major leap in clinical genetics, that we can give patients a diagnosis, and that will help to personalize the treatment and care. We have done in Sweden now more than 10,000 patients, and there are 3 sites in Sweden, 3 genomic centers, medicine centers that provide clinical whole genome sequencing. In cancer, if we start with blood cancer, we have used genetics for decades to risk stratify and select treatment. We agreed upon a national panel with almost 200 genes, and that has been implemented successfully at the 5 genomic medicine centers in Sweden. And in the beginning, I was a little bit afraid that the clinicians would think that 200 genes, the replies on 200 genes would be too much. But actually, it has worked out very nicely, and we have a very good and tight contact to discuss how we can improve the reporting and etc. And right now we have an ambitious project in Sweden where we perform whole genome and whole transcriptome sequencing in all patients with acute leukemia during 1 year. And we have so far included 100 patients out of 450 patients, and this will be very exciting to follow. So far it looks like we can really detect everything that we need to detect with standard methods, but now we can exchange a number of different methods with one technique. For lung cancer, we heard this, and we have seen Karin also before. In lung cancer, we know that there are many targeted treatments, and there are many different genomic aberrations that we need to detect in order to give the right treatment to the right patients. And within Genomic Medicine Sweden, we are launching a 560 gene panel, which is for all cancers, we will have separate panel. We have separate panels for blood cancer, but this is for most solid tumors. And this also panels can also detect more complex markers that is important to know if immunotherapy for selection of immunotherapy. And we also have a national program for children with cancer where we started to do whole genome sequencing. And so far we have included 100 patients, and this not only shows gene aberrations connected to different targeted therapies, but we can also find children with a predisposition to cancer. It's estimated that at least 10% have a predisposition to cancer. And to the right, you see a young boy, Wilfred, who had an ALK mutation and got ALK inhibitor, and he has responded very well to this treatment. So this was my last slides were focused on the diagnostics. Of course, we need to be able to offer therapy also for our patients. In Sweden, we have a study called Megalith that is a combined umbrella and basket study, and they include patients now at 2 university hospitals in Sweden, and they have signed an MOU with different precision therapy studies in the Nordic countries, but also with the drug repurposing study in the Netherlands. And I think this is one important way. We need to work with precision therapy studies within the country, but also with other countries, especially for rare cancer types. And in Stockholm, the Karolinska is part of Cancer Core Europe, which consists of 7 comprehensive cancer centers, and together they are performing the same type of gene panel diagnostics, and then they have this basket trials where they include patients. So independent where they live in Europe, they can be included in a basket. And they just got the paper accepted on the first 500 patients. This molecular tumor board portal that is used to decide if there are actionable mutation was developed at the Karolinska by Janne Lehti's group, and they now summarize the experience from 500 patients that is published in Nature Cancer. And one very recent development is the new innovation milieu for precision health in cancer, Testbed Sweden, that Ebba is leading. And here we have joined a number of, this is really co-creation. I think it's 15 different stakeholders that come to the same table to discuss how can we facilitate national personalized cancer medicine studies. So this will be very exciting. It's a 5-year project. We have developed, or we have published our 10-year strategic plan for genomic medicine Sweden, which is of course to continue to offer broad gene sequencing, to use the national genome platform as a knowledge database. Of course, we should make use of the data also for new research and innovation, and really push for more national clinical studies in personalized medicine. And of course, what have been discussed earlier today is early detection and prevention, which will be very important also in the coming years. So what we have learned, we need to work on a national level and also on an international level. So I think it would be great if we can have contacts with the Emirates after this meeting and discuss how we can collaborate. We are collaborating with a number of countries over the world, and that is also very exciting. Not always that you do projects together, but just to exchange experience is very important. And as had been discussed this morning, we also need to work at the regional and local level. So Anna Mattling presented the Precision Medicine Center Karolinska, which is a joint action to really move precision medicine into patient care. So I think you need to have all these levels in order to be successful. Of course, I have focused a lot on diagnostics and treatment, and you may excuse me, I'm a clinical geneticist, so I've also focused a lot on genetics. It's not only genetics. You need a lot of different other omics data, image data, patient-reported data in order to really realize the full potential of precision medicine. And then with prevention, which will be very important, and you heard this morning exciting development like the Stockholm 3 test and the GRAIL test, etc. So I think this will be an exciting future with precision health. So let's co-create. Thank you very much.
Thank you very much, Professor Rickard Rosenqvist-Bramrell, and thank you very much also for promoting our new initiative for the implementation on a broader scale of precision medicine. And we'll come back to that with our distinguished panel in a moment. One thing that we discuss a lot in Sweden, which is not unique for Sweden, is of course the access to data and also how you share data and the use also of new technologies and artificial intelligence as critical enablers for this modernization of the healthcare and particularly cancer care. And it's also a prerequisite for equitable access. So Richard, please stay online with us and we'll come back. I would like now to invite to our screen live from New York, I think, or Baltimore probably, Johns Hopkins Medicine, our next keynote speaker, Professor Dr. Wilfred Nungawa, who is Associate Professor of Radiation Oncology and Molecular Radiation Sciences, who will discuss AI, big data and equitable access. So please welcome Dr. Nungawa. The floor is yours.
All right, thank you so much. I'm very grateful for this invitation. So today I'm going to talk about AI, big data, and equitable access to cancer care. Okay, so, I always like to start by talking about, the cancer statistics, which, drive us each day to kind of think about, why we get up each day and go to work. So I work in oncology, as you know, and obviously artificial intelligence and big data has some really great applications in this area. So I always like to start with the statistics. So as you know, according to the recent World Health Organization report, over 18.1 million new cancer cases a year, over 9.6 million deaths a year. And a lot of these have major health disparities. Since we're talking about equity, we know that 60 to 70% of cancer incidents and deaths now happen in low and middle income countries. We actually have similar disparities in the United States. I just give you an example, for prostate cancer deaths are 3 times higher in people of African descent. And so there's a really great opportunity to look at how we can leverage AI and big data to address such disparities. One of the major drivers of disparities is what we call the Great Barriers. So there's geography. So depending on where you were born, where you live, that could be you may just live in a low resource setting, maybe in a country that's poor. And so that is a great driver of disparities. We also know about race, your income, attitudes and culture, and of course, technology. And as in the past speaker just shared, we can actually use a lot of the AI technology that we have today, to drive personalized medicine. But I also, because I work in radiation oncology, I'm a little biased to think about, what the magnitude of disparities are also in this area. So if you look on this map represents, from the IAEA, it represents, the disparities or inequity in access to cancer care for radiotherapy. You can see all the red regions that you see on this map are, areas where they have less than, one. Some countries don't even have any radiotherapy machine. And just for context, radiation therapy is used to treat over 50% of cancer patients. So if you think about somebody living in these regions, they don't have access to this. So a lot of this is in Africa and Southeast Asia, but also we see in Eastern Europe and some regions in South America that this is a big issue there. I read an article some time ago in the BBC, British Broadcasting Corporation, that do US docs have better access to radiotherapy than Nigerian people? And this was really a provocating question, but the sad answer to that is really true. And the question is, if you look at this magnitude of disparities, how can we address this? One more disparity that I would like to highlight is in human capacity. And this is really true also for when you start thinking about artificial intelligence, as I'll share that in a moment. So in medical field, in oncology, there's a great need for human capacity, equitable distribution of that. And so education and training is really important in this area. So in the spirit of thinking about this excellent conference towards Vision Zero Cancer, as we think about that, big question is, how can artificial intelligence and big data help to achieve equity? So I want to start by kind of looking at these what the problems are in terms of artificial intelligence. So a lot of these obviously have to deal with, you have to think about the data. So most people have major issues right now in access, in resource poor settings. Access is limited. You have work health shortages, as I just mentioned. You have equipment shortages. You have drugs shortages, and there's poor data collection. I was born in an African country called Cameroon, where if you go to most of the hospitals, the data there is still in paper form. And things about electronic health records and the data that you can actually use for artificial intelligence applications is not there. And then you start thinking about the challenges. So the big challenges to AI, globally, is to think about, people don't even understand the true capability of AI. So there's what we call AI literacy. You want to think about artificial intelligence talent. There's need to train a lot of people. Good enough, right now we know from surveys that most low resource poor settings countries really are interested in artificial intelligence and going to school to learn about this, getting the training that's needed. And there's a huge talent there. It just needs to be trained or to be leveraged for this. And then the other challenges that we have are regulations. So basically, most countries don't still have the right regulations. Even like we had in precision medicine, there's really need to collaborate and share data. But the regulations don't really have good uniform policies right now. So they need to really revise this. We think about funding, investing more in this direction, infrastructure, things like that can provide you with the needed, information, electricity, internet, and data digitization that you can use for artificial intelligence applications. And so when you start thinking about what are the AI applications that you can, application areas that you can leverage for equity, then you think about portable diagnostics. So this is a very easy one, that people can use for, cancer prevention, low-cost devices in community centers and households. You can also use artificial intelligence to address healthcare worker shortages, patient triage, compliance prediction, and then even more important for the areas for those of us who work clinically, is to think about how you can develop clinical decision support tools for physicians. I know one of the companies like Elector, have actually, there's the whole concept that, partnered with IBM to look at how you can use artificial intelligence to troubleshoot equipment failure and predict, which is really useful because a lot of this infrastructure like that for treatments. You can predict when they're, you can take measures to mitigate any risk if you know what's going to happen in the future. But I think a big part of artificial intelligence in population health is really where a big part of the impact will have. We will have that impact in looking at health registries, in epidemics controls. With COVID-19, a lot of artificial intelligence applications have been developed to predict such pandemics and things that happen to increase access and eliminate disparities. So this is really important to see the scope of how AI application can really benefit healthcare. Just a couple of more slides to kind of show, as you think about big data. So obviously, a lot of these has to do with how much data you have, and the different levels of that. At the population health registry, it's kind of easy to get data in that direction, electronic health records. But as you think about, going more specific to treatments, it becomes more limited data that you can use for AI applications. And so that's where collaborations become really, really important. This is going to be an area where we really need to grow as we look at big data in addressing disparities. I also want to share this because I think, in treatment decision support for patients, there's a lot of it's really important that there are different levels where you can apply artificial intelligence. You can start from, diagnosis to consult to simulations or imaging of patients. In radiotherapy, we use that for contouring. I'll show some examples of how this can be leveraged, to make the task easier, facilitate treatment decisions, and all the way to actually follow up for patients. So now we have federated learning models that people can even use for their mobile phones. And so this is really a great area where big data can actually be used in radiation therapy, one of the areas where this is really growing. So in the last part, I'm just going to share, one of these new initiatives that has, you can imagine. This was actually launched with support from IBM. And the idea that you can create a cloud, a comprehensive cancer center in the cloud, where everybody, can have access to it. And this can really overcome some of those great barriers I talked about at the beginning. So think about geographic or distance time barriers. You can be in Sweden, or you can be in the United States, or you can be in Africa, and you can still have access to this. So, that can really be a great way to bring equity, to alleviate disparities. And so, patients can access that, educators can access that. So this was something that was launched at one of the global health summits that I direct at Harvard 2 years ago. And so a lot of the components of this are coming together, and I'd like to share some of that, some of what this concept really means. So you can think about this, you think about a mobile phone or connected to the cloud that has 4 apps on it. You can see applications of artificial intelligence in education and training. Remember in the map, I talked about the challenges that artificial intelligence faces. One of that is in training. And so there's a huge opportunity where you can train people, but then you can also, leverage technologies like this to educate people as well. And so we've actually developed this global oncology university platform for radiation oncology that can train, and educate people on AI, and at the same time, facilitate collaborations. Another opportunity here, of course, which is has been really grown during the COVID-19 pandemic, is teleoncology, where you can have artificial intelligence support. Again, in resource poor settings where you may have just one physician or doctor, you can see a great potential for application here because, they can have, somebody to assist them in their treatment decision making. Whether it's looking at their genomics or pathology data and making predictions for the treatment, the best treatment regimen. You can think about how that can really be useful. And one way that we're actually using this now is in clinical trials, to support ongoing clinical trials. You can use that for recruiting patients. You can use that for, helping with the quality assurance and treatment planning, making sure that it's uniform across the different centers. So there's a great opportunity where you can apply artificial intelligence in such research. And so, this is, I just want to end by sharing an example. So this is really one where, we've been able to apply artificial intelligence in clinical training, but that also impacts the care. So in this case, we actually used a technical platform called Prono that's is currently owned by Elekta. It's a Swedish company. And obviously, what we see there was that if you look at this diagram, artificial intelligence has been trained essentially to be by experts so that it's now become the expert. And so we were able to offer this to doctors in Africa, and they were able to practice or to learn how to contour. Contouring just means that you get the CT images from cancer patients and you have to look at where, before you deliver radiation therapy, where is the cancer and where are the neighboring organs that are healthy that you don't want to treat. And so you can basically, we had, doctors across Africa just use this technology to contour, to map out where the cancer is. And then the artificial intelligence was able to guide them or to match that with the expert contours. And that was a really high impact program that benefited a lot of the doctors. And I just show you some of the data that we have. We kind of show the skill levels and competency for these doctors. And it was good and bad. So at the end of the program, we thought, wow, this is a great improvement in the skills. But at the same time, it was, wow, what have these doctors been doing so far with patients? And so you can really see an example where, you can use such technology, platform with artificial intelligence to help, educate. But you can then take this further, to help using the same tools. You can use that to help facilitate treatment decision support for these doctors, because they may be working by themselves in their clinic and they just want to get a second opinion. So, what I hope to have accomplished here is to show you that there's a lot of potential for AI in addressing disparities with these examples that you can see. I say in Africa is one of the big targets for the future for this, because people may not have toilets in Africa, but they do have mobile phones. They're not yet all smartphones, but you can use a lot of these artificial intelligence and cloud big data. You can use that you can imagine how different applications can leverage these mobile phones. And so, establishing the comprehensive cancer center in the cloud, we actually think that we can use this even with federated learning models where, patients can own their own data on their mobile phones, so you can kind of sync that into the cloud, and they can continue to learn. And you can use that to increase access to care. I should say that to end that there's a really great need for policies. As you look at resource poor settings like in Africa as well, most countries don't have the right regulations yet. So that really needs to be addressed. People need to be trained. And even more importantly, I think there's need for collaborations with countries like Sweden, with European countries, with countries in the United States, because a lot of the artificial intelligence tools, I was talking to somebody yesterday from Nigeria who said, a lot of the artificial intelligence tools have been trained with the data. They've been trained with data from Europe and United States. It needs to be trained also with data in resource poor settings. It has to be, like in Africa, where you have to use that for the patients there or for the people there. So there's great need for collaborations to address these disparities and to increase access to cancer care. So thank you for your attention, and I'll be happy to take any questions.
Yes, thank you so much, Dr. Nungawa. Very, very inspiring, and indeed call to action to collaborate. And it's great to see we already have the tools and the possibilities. Now we just have to do some leapfrogging and come together across the globe. And the shortages and some of the critical assets that you were mentioning, we have them in all societies with a shortage of staff and train going forward, not the least when it comes to radiation therapy. So this type of education and different initiatives are so important. And our distinguished panel that we have here waiting to join the stage in a little while will definitely reflect upon your suggestions and definitely talking about the comprehensive cancer centers in the cloud. So thank you so much, and we look forward to strengthen our collaboration going forward. Thank you.
Thank you. Thank you very much.
So now it's time for a guest on the physical stage here. So please welcome Dr. Boratas. He's a doctor in medical physics, associate professor, physicist, director for the MR-Linac region with Turkey, India, Middle East, and Africa at Elekta. Welcome. The scene is yours.
Thank you, Emma. Good afternoon, everyone. My name is Boratas. I'm leading the Linac and MR-Linac business line in region TIMEA at Elekta. So I would like to talk about the rapid innovation of radiation therapy technology. So as you know that Elekta is really innovative company in the radiation oncology field, and Elekta was founded by Lars Leksell, and who has been well-known neurosurgeons at Worldwide. And we are going to celebrate our 50th year anniversary in 2022. And also Elekta has dedicated itself to pioneering advancement for cancer care. And we have a really comprehensive solution for the cancer treatment. And unfortunately, the cancer incidence is on rise. And if we look to also geographically, you can see that the most common cancer incidents are prostate and lung for males, and also breast and the cervical cancer for females. And we expect around like 24 million new cases in 2030s. So the numbers are really increasing rapidly. And patients has still lack of access to radiation oncology. Actually, if you look to total average optimal utilization rate is around just 50%, and the identified clinical need for linear accelerator is twice number than the existing install base. So the main gap is coming from the emerging market. So the access to radiotherapy is really key factor for treating the cancer patients. So when we look to also history of the radiotherapy, actually in 1920s, it began with the low voltage X-ray beams for treating the superficial tumors. But for treating the deep tumors, the beam needs to penetrate more in the tissues. Therefore, end of the 1930s, they have reached to mega voltage level X-ray beams, and they started to treat patients in late 1930s with the mega voltage devices. And as you see that those sculpting from that time until now significantly changed. So because of the technology impact, and actually in late 1990s, when the CT simulator involved to radiotherapy workflow, the main change became at that time. Because after the CT simulator, we were starting to use the treatment planning system. It means that while getting a three-dimensional images, we could do the 3D conformal planning while sparing organ at risk and while hitting our target. And later on, even Elekta launched first CBCT system in 2003, because image guidance is also very critical for treating the tumor. Because you know that we are using external beams while treating the patients. These external beams can go to other organ at risk as well. So we shouldn't increase the toxicity level. Therefore, image guidance is really playing a very big role for the radiotherapy treatment. And after that, also Elekta implemented the volumetric modulated arc therapy around 2007, and we started to manage very homogeneous dose distribution at the target while sparing organ at risk. Therefore, we have started to increasing also the doses at the target. Before it was not possible. And in 2018, also we launched the state-of-art technology, which is MR-guided radiotherapy. Nowadays, 1.5 Tesla and next generation of the linear accelerator are together in the same platform. So when you see clearly your target and organ at risk, it means that you can reduce the margin. When you reduce your margin, you can protect the organ at risk in a better way. And another important thing is nowadays we can do the adaptive planning. The reason that in day by day the anatomy is changing. So when you get a new images, when you are making a new adaptations, it means that you can protect the organ at risk in a much more better way. And another also important thing is that with the existing system based with the QV images, but when you want to give the QV images to patients during the treatment, then you are giving additional irradiation doses. But with MR-guided radiotherapy, without giving any radiation to patients, you can monitor the treatment without giving any damage to patients. So therefore, your treatment quality could be much more precise than before. So when we look to also 5-year cancer survival rate in the US from 1970s to 2016, as you see that in most of the cases, the cancer survival rate increased for 5 years. In some indications, you can clearly see that more than 80, more than 90% we have a cancer survival rate. On the other hand, still in some indications like pancreas, liver, esophagus cases, we have really poor cancer survival rates. But in the pancreas, in my next slides also I would like to talk about the MR guidance radiotherapy can also increase the survival rate due to the reducing the margin of the target and sparing organ at risk. Therefore, we are capable to increase the doses at the target. So this is the total body irradiation from my clinical experience. Until now, we were using also some conventional techniques, and we were considering that whole body is homogeneous, all tissues are the same density has, and even all body has the same thickness. But in reality, it's not true. So the neck part of the body and the abdomen part is completely different thickness, and also the lung, also the soft tissues and bone area has also different electron density as well. So it is impacting the dose distribution. So also while using our Elekta linear accelerator, we can use the volumetric arc therapy when the patient's on the couch. So it means we can reduce the toxicity level of the patients. Why we do the total body irradiation? So we have a threefold. One of them is the eliminate the residual cancer cells, and another one is the opening a space for the transplantation, and other one is that immunosuppression, because these patients are going to the also marrow transplantation. Before that, they are coming for the radiotherapy treatment. So it means that we are not treating just the solid tumors, we also treat like leukemia cases, lymphoma cases, plus some brain disorders, as you know, benign tumors, and even nowadays some clinics are treating ventricular tachycardia patients as well with irradiation. So it means that the radiotherapy incidents are getting wider and wider with this precision. And if we look to clinical trends nowadays, the immunotherapy and radiotherapy combination is really making sense. It is increasing the efficiency of the immunotherapy in some indications, and hundreds of the current trials are ongoing about this project. And another one is the oligometastatic treatments. And nowadays the life expectancy of the patients are getting longer and longer, and these patients are coming for the secondary irradiation. So before we were not seeing too much, but nowadays these numbers are increasing, especially while using the MR-guided radiotherapy. Even very tiny tumors you can easily see with the 1.5 Tesla MRI. And of course, the integration of imaging is really helping us, because when we see clearly the tumor and organ at risk, we can protect organ at risk and we can reduce the toxicity level of the patients. And another trend is the hypofractionation and SPRT. As I mentioned that we have a limited number of the devices in worldwide. So hypofractionation and SPRT means we are reducing the treatment courses and we are increasing the daily doses to the patient. So instead of coming to 39 days to department for the prostate radiotherapy, these patients are coming just 5 times. Even some sites like Royal Marsden are working for the 2 times treatment. So it means that you can use the machines much more effectively, then you can reach the more patients while using this hypofractionation and stereotactic capability. And also related with the MR-guided radiotherapy, this is also a new era, I believe. Actually, as you see that with the biomarkers may change the radiotherapy from one-size-fits-all to personal approach. The reason that not all tumors are giving the same response to irradiation. Some tumors are giving more, some tumors not giving response. So it depends on this response, we might de-escalate or escalate the doses. Because with the MR-guided radiotherapy, we can get diffusion-weighted images and we can get also ADC map values. While getting this information, even during the fractionations, you can monitor the treatment response. You can differentiate the post-therapeutic changes, and also you can predict the treatment outcomes. If you see that the tumor is not giving response, maybe we will send these patients to the alternative solutions, maybe surgery, maybe chemotherapy, maybe immunotherapy, but this is really opening a new era for us, predicting the treatment outcomes before finishing the treatment. And even if we would like to do some tumor characterization and staging, it is also possible with the 1.5 Tesla diagnostic MRI inside of the linear accelerator. So this is from one site in Istanbul with Unity MR-guided radiotherapy treatment. Pancreas is really important incidence, and as you know that the poor rate, the cancer survival rate was so poor. The main reason that if you use the CT images or CBCT images, you cannot see clearly the pancreatic region because the duodenum and too many critical organs are very close to the pancreas. So therefore, when you have a 1.5 Tesla high field MRI, you can clearly see the pancreas, duodenum and organ at risk in a daily basis. So you don't need to give additional margin, then you can reduce the margin and you can do adaptive planning each day. And nowadays some sites are giving around 40 gray or even 50 gray in 5 fractions. It means that with the conventional system you cannot get to those levels, but with the MR-guided radiotherapy you can easily reach this level. Even during the treatment you can see that you are not missing the tumor. Before with the conventional system we were assuming that we are hitting the target, but nowadays we are quite confident that we are hitting the target and we are not missing. So that's why even in the literature ongoing trials are ongoing, and it's clearly showing that the cancer survival rate can improve with the MR-guided radiotherapy. So this is also a very important feature of the MR-guided radiotherapy. So when we got the first cell phone, we were using just for calling each other or we were just sending SMS to each other. But later on with the smartphone, with many applications, our life is much more easy and comfortable than before. So even I believe none of us was thinking that in 10, 15, 20 years later, this kind of the application we could have it. So the same things for the MR-guided radiotherapy, now it is available and we believe that it will open new era for the cancer treatment and the radiotherapy goes in a personal approach instead of the all fits to everyone, because all tumors are different, all patients are different, and while getting a MR-guided radiotherapy during the treatment, getting an information about predicting the treatment outcomes, and also our anatomy is constantly moving, and real time we can see what's happening in the anatomy. So these kind of new innovations are really opening a big era for the MR-guided radiotherapy. Thank you for your attention.
So thank you very much, Bartosz. More exciting opportunities that the panel will have the opportunity to reflect on in a moment. But before we go into that, we will have a couple of cases shown here on the screen. As we talked about now, the personalization of cancer care means actually creating this holistic approach from early detection and the prediction, improving also the methods for screening to make sure that we can select with the right quality. And one case that we would like to show from Sweden, from the University of Lund, is about using 3D mammography for screening for breast cancer. So I would like to welcome on a video Dr. Sofia Zachrisson from University of Lund University Hospital.
The results are really encouraging. We found 34% more cancers with 3D mammography or tomosynthesis compared to regular mammography, which is a huge difference, of course. In tomosynthesis, the X-ray tube moves in an arc over the breast and acquires a number of low-dose projection images. And then this information is reconstructed by computer to very thin slices of the breast that the radiologist can view on a screen. And it means that we can more easily see where a tumor is in the breast. We used reduced compression during the tomosynthesis, which means that a lot of women liked this method better because it was less painful. And hopefully, if tomosynthesis will be used as a screening method in the future, it could encourage more women to attend screening. We did not only find more cancers, because with a more sensitive method, you also see a lot of other structures better in the breast. Since we didn't have any comparisons from before, we had to call back those women for further examination to exclude that they actually had a cancer. So the callback rate increased. In the majority of cases, the cancers detected with tomosynthesis, they were invasive cancers. And this means that it is cancers that has the ability to spread outside the breast. And this is an important aspect because we want to find the relevant cancers in a screening program.
Another example of what science can do. Another solution is about how do we match the right patient with the right therapist. So another solution by Acrivon Therapeutics.
My name is Christina Masson, and I am co-founder of a company called Acrivon Therapeutics. I am a scientist by training and have a PhD in molecular signaling. Our technology matters for cancer patients and their families. Our technology platform allows for precise matching of drugs to the patients that will benefit. The main attrition factor in drug development in cancer today is lack of efficacy. The industry is very good at producing safe and precise drugs, but not so good at identifying who the patients are that will truly benefit from these drugs. Our technology platform is aiming to solve precisely that, to identify the patients that will really benefit from our drugs. Our technology is based on high-resolution mass spectrometry to identify drug-tailored biomarkers that predict response to different drugs in patients. Our unique platform is called AP3, and that stands for Acrivon Predictive Precision Proteomics, and is based on phosphoproteomics, where we extract information from large data sets using computational methods to identify a small number of actionable markers that can be measured in a simple biopsy prior to treatment in a patient in order to learn whether the patient will benefit from the drug or not. Our company has been part of the SMILE community since we started and has truly benefited from the scientific infrastructure and expertise here.
So, thank you to Acrivon Therapeutics. This morning we had an exciting panel talking about redefining around research and innovation with the patient at the center. And one of our partners on stage was Cellink, working with bioprinting. And I would like everyone who's here today in the Sweden Pavilion at EXPO 2020 to come down later on to the co-creation stage where Dr. Itedal Namno and her colleagues will showcase with the bioprinting. So now, dear friends, it's time to actually invite a panel to reflect on the challenges and opportunities to the global adoption of personalized cancer care. So I would like to invite the five of you coming up here now. We have Dr. Humaid Al-Shamsi, professor, founder and director of the Medical Oncology Service at Burjeel Medical City. You were here before also discussing the adoption of prevention. Dr. Sahid Al-Mandari, from head of Radiotherapy Department at Gawas Comprehensive Cancer Center. Dr. Björn Swega, CEO of Karolinska University Hospital in Sweden. Dr. Frida Lundmark, head of the research-based pharmaceutical industry in Sweden. And Dr. Bettina Ryll, who you also met this morning, patient advocate with the Melanoma Patient Network Europe, and also member of the Vision Zero Cancer team, and also on the first mission board of for the European Union. So, welcome all of you to the stage. I would like us to see if we could start by reflecting on what we see as the main priorities for addressing these challenges, and perhaps reflections on the round of the different solutions and discussions that we've heard this morning, and also now in this session here. So I would like to start with Dr. Humaid Al-Shamsi. How is the access to personalized cancer care right now in the UAE, and how do you see the progress going forward?
Thank you for the question. I should say that I was very impressed with the national program in Sweden. I didn't think that any such program exists worldwide, because we understand the challenges with such novel way of treating cancer. If we talk about the UAE, we're still in the infancy stage. We're still in very early stage to adopt such program across the country. Currently, the personalized medicine or testing for genomic medicine is highly, restricted, not widely accessible for everybody in the country. And we're still trying to navigate this with the regulators and also with the insurance company, trying to showcase that, it does help, it does, make a difference in patient life. In fact, we are currently in the process of collecting data from across the countries in patients who had solid tumors and hematological malignancies, and to show that, this has also impacted their survival. So we are still in the infancy stage, and I'm very happy to hear about your experience, and definitely I'll be more interested to collaborate more, to learn about this experience and how can we accelerate the process to adopt such, genomic medicine in the country in UAE.
Excellent. And perhaps to you, Björn Swega, being part of setting up all these initiatives also in Sweden and with the region Stockholm. A reflection from you.
Well, the reflection is that we are sort of, what I used to say, the future is here. We're doing this now, and when you start doing this, you run to other problems than you thought you would have. And that leads us to regulatory problems. Where can we store the data? How to use the data? We haven't solved that. So all these regulations, they're way behind, and they will probably, I will not say kill this, but they will slow down this initiative by far. And things like that, we in Sweden cannot store any of the data in a cloud. We just got about a month or two ago a regulatory change in the wrong way. So we cannot use the cloud, even if the cloud was situated in northern part of Sweden. So there are some things that we need to do, and even though we're well ahead and going forward with many good projects or using them in the for the patients as a regular care, and we can talk about our project that we now do all the biopsies that are looking for cancers in colon and rectal areas. They get the same treatment. They'll get a sequencing actually by a panel, which is also another problem, that we have not certified the whole genome sequencing or the exome genome sequencing. So we're still, because we're moving that fast, not everybody else isn't moving that fast. So we have to get people on the boat. The last thing I want to mention, I'm talking about problems now because we're in the future. It's still not solved, the big hurdle. This will cost more in the beginning. In the beginning. So letting the society know about that, getting the politicians that are representative of the society to understand that and see there will be a long-term payoff, not only in money but also in lives.
Exactly. Actually, in a moment we will actually, perhaps we could do that now. We do have a mentor question that, because one of the hurdles is of course the access to financing and to funding, and also how by the developments and the incremental use of testing, genomic testing, but other tests, actually it's becoming affordable. So that's one of the hurdles, and also to break through. So perhaps if we could have the mentor question up here now, we could as well continue addressing the hurdles around the financing. So you see, approximately 20 years ago, it was more than $95 billion dollars. $1 million to sequence the human genome. How much does it cost today? $1,373, $562, or $784 as an average. I'll give you some time to think of this.
Yeah.
It's 10,000.
Depends on your healthcare provider.
Yes.
It depends on your healthcare provider. We heard that one, Dr. Bettina. Of course, it's a global average here now.
So
what do you think?
I could give you an example.
Yes.
What does a panel cost that we use for the colon and rectal cancer? It costs 3 times more than the whole genome sequencing.
Agree.
So then I think Dr. Björn Swecare is revealing the answer here now to this mentor question. So I know with the live streaming, we give a few more seconds, but it seems that everyone's well informed showing this. So it's been a radical decrease, of course, in the volume. So $562 on average. So at least the access to that type of genome sequencing, and then of course you have to do more with that data, is already, I think, one of the barriers that we are eliminating by now. And then of course there are more parts and hurdles to address, of course. And any other reflection on that when it comes to that part of it with the financing from anyone in the panel? Perhaps, yes, Dr. Ellenmark.
So I think it's important to remember that is sort of the diagnostic part.
Yes.
Then you need to have the next level added to it, that when it comes to treatment. So we need also to find the models to use the diagnostic data for profiling, and then profiling that against the available treatment.
Yes.
And I think that is sort of the pipeline that also needs to be set up. And then you can look at the cost in a total, maybe. So I mean, it's important to see the whole system here around precision.
Definitely.
If we're talking precision health, because then we also includes the public health and also the prevention part. So, so that is just to remember that we need to add on the treatment in the next level.
Definitely, and all the different treatment modalities and combined. And thinking, coming back in now, Doctor, with the radiation therapy and also the access, and also now with the new imaging technologies enabling new possibilities for treatment and cure. Perhaps you would like to elaborate on that.
Yes, with regards to radiation therapy, obviously we've started with discussing precision therapy, but as you've seen that we've gone from literally just giving radiation to a box to being refined to more a nice sculpture that you see. But that was all based on assumptions that things don't move, things don't change, and what we see on CT scan is what we're going to deliver on a patient. And the reality is that patients don't stay the same. They're not the same on the same day, they're not the same after 15 minutes, they're not the same in every other fraction. So when it comes to radiation, I think we also need to think outside of the box. Even with MR-Linac technology, where we're now seeing what's happening to the tumor, what we're doing now is gating the treatments, stopping the treatment when the tumor is outside of the field. We need to look at using artificial intelligence to predict motion, to understand how the tumor is going to move, and use the imaging as a confirmatory of what's actually going to happen. Because you can't image and then say, okay, oh, you're here. That means you've missed part of the treatment. So it should actually be a predictive model looking at how tumors are moving, and that would give us a more accurate targeting of a tumor. But we also have to think on another aspect. We've talked about genomics, and a lot of times when you talk about genomics, we talk about drugs. But we haven't actually talked about how genes affect radiation. And that's really somewhere that we need to really explore. And I think that's really, we're way in the infancy of figuring out what genes or what characteristics of a cancer in terms of its genomic makeup make it a suitable candidate for, say, radiotherapy versus a drug that can be a targeted therapy like immunotherapy, etc. So I think we're still not yet there. We need to break out of this thinking. One aspect just I wanted to add to it is industry tends to dictate what happens in radiation and regulation. Sometimes when you need to have clinicians involved in the industry to push the boundaries of what is possible. And we do have the tools out there. When we talk about big data, artificial intelligence, it's all there. How do we put it in one package so that we can give the best treatment for our patients? This is a little bit of a hurdle that I think is stopping us. We're not thinking of using that information in a correct way.
Comment from you.
Yeah, just want to add on, because you said radiation and chemotherapy. Don't forget surgery.
Yes.
Because some of the personalized medicine, some of the genes there make, if you go it the wrong way and do the surgery before the chemo, they have a worse outcome. So we have to think about all three, and the personalized medicine is for all of them. So that's really sort of getting the holistic picture.
Yes, absolutely.
Perfect. Dr. Bettina really wanted to comment here, and then to Frida Lemark.
To think back, and actually I would like to quote you that you said, I love that. We first have to get the basics right before we move into the technologies. And when thinking about personalization of medicine, I think we often get very soon stuck in genomics or a very precise technical detail, and usually I quote this as expensive diagnostic to an even more expensive treatment. However, if you think about it, you can personalize anything in medicine. You can personalize any procedure, and you can be coarser or more refined in the way you personalize. Yesterday we had a panelist here who argued very eloquently that there are differences between men and women in the way they react to drugs, and she mentioned metabolic differences. But if we look at response to checkpoint inhibitors, the latest immunotherapies we've also been hearing about today, women have a different type of response to immunotherapy. And biologically, that makes total sense. You would never be able to carry a child otherwise. But we never look at that. And that's a simple stratification rather in that sense. You can also stratify or personalize services. ASCO 2018 had a big discussion in the panel showing that simply reporting, and we had the colleague from Kaiko here earlier today, letting patients report on 5 simple items on their quality of life, and those were patients with advanced cancer and last line of treatment, and calling in those who showed a deterioration of their quality of life in earlier for an earlier follow-up, was able to prolongate their lives without the introduction of any novel therapies. What you personalize in that way is the follow-up process. So that's also personalization without new fancy things that improve outcomes. And we should, in my opinion, we should be doing this. So there's a conceptual thing. The next one is what I call the catch-22 of personalized medicine. So personalized means we think genome, me, myself, and I, we look inwards. But what we have to understand is that in order to find the patterns that will predict what works for me, we have to analyze large data sets. And the more we want to personalize, the larger the data set has to become. And the problem with this is the way we generate evidence today, it does not work anymore. So in order to get the data sets that we need to personalize, we first have to implement, because otherwise we never get the data sets of that size. But we don't want to implement, because we don't have the evidence yet. So we are basically turning in this catch-22 that we are biting our own, we're chasing our own tail, and that we have to solve if we really want to make progress. And the last but not least, and that is on connecting minds and collaborations, I think we have to really sit down and really think about the incidences of certain cancers in our societies and how large our data sets have to become if we really want to provide care for everyone. I've been looking into rare cancers. 1 out of 4 patients has a rare cancer. So each one of them is rare. As a group is 25% of all cancers. All our countries are too small to provide, if we just think nationally, to really help 1/4 of our cancer patients. If we don't want to give up by default because we can't think about it, then we have to think from the beginning, big, global, and that means we need an interactive and standards, and that all of a sudden is not personalized anymore, that is strongly harmonized. So I think it is these different levels about the concept, how we get the evidence we need, and then to the scale of collaboration that will make it even just simply possible. That I think that is, for me, this is the critical steps that we have to get right if we really truly want to adopt precision in medicine at scale.
And Frida, what do you say here in relation to this?
Yes, and I totally agree with you. And also on the concept of what is precision medicine or what is precision health. For me, it's sort of a higher granularity. You get a higher granularity in the diagnostics, in the treatment all the way, and something that will inspire the whole healthcare sector within maybe, not exactly now, but throughout time. So we will not talk about precision medicine in 10 years because that is the healthcare in 10 years. And also, I think that what you say, that it can be personalized, but also in the population level. So you can see it regarding if you are in the really rare disease, then you maybe have the whole genome sequence and identify the specific target gene that is, or the mutation of that individual. But when you're looking at diseases like type 2 diabetes and cardiac diseases, you are in the bottom where a large number of individuals in the society will be affected. There you look at other types of biomarkers and do substratification and subphenotyping, and that is precision health or precision medicine on another level. So I think we need to sort of divide this into different parts, depending on the incidence and prevalence of the diseases. They need different types. And then I will come back to what you say about integrating things, because I think it's very important to remember that to be actually implementing precision health and precision medicine, we need to not look at the genomic profiling, the imaging, the proteomics separately. We need to be able to integrate those and do the collective analysis of all those type of data together. That's when we have precision health and precision medicine for real. And then we have the challenges that you mentioned. Where do we store the data, and how do we find the decision support systems that helps the clinicians to understand what does this huge amount of data really means, because that is also tricky. So there is enormous potentials in this, but we need also to be able to connect the dots a little bit better.
So how could we go about connecting the dots better?
So I think this is an area that we most certainly needs to work together. We need the academia, we need industry, and we need the healthcare system and the healthcare sector, and we need to work together because we need to capitalize on all the competence and knowledge that we have from all different actors to really drive this forward.
And also the way of developing new therapies, generating new evidences, and we see also in a country like Sweden, we have a population of 10 million. Many cancers like lung cancer is suddenly becoming a rare cancer. There's so many diagnoses now. So also then to treat, we need to also to have further collaborations also in that respect. I think when it comes to how we treat and how we can create that opportunities working together across borders. So please weigh in on this one. I think also at you at Karolinska University Hospital, you have many also international collaborations and the outreach, and also as Rika Rosenqvist from Karolinska and the Genomic Medicine Sweden initiative also highlighted.
So yeah, we have that, and not only in cancer, but also with the rare disease network.
Yes.
We have on a European level, and that's because of all this. Well, all this data that we are getting now, it's going to be difficult for just us to look at it. It will sort of, when you have rare cancers, you have to be able to put it out somewhere, so at least some of the data then say and call for. Do you anybody else has any cases like this? We get one every 2 years. Where's the other? And pull together some kind of that. And we need to also see the really big opportunity that we have to move medicine further in finding new things when we get all these data with all this gene information and the patient or somebody related to the patient gets another disease later down the road, that you can do some research, go back with the biobanks and so the opportunities of discovering new cures and new things is huge. But it's the big data thing has not really been solved. This is sort of a thing that we need to solve going forward.
Exactly. So I think we need to invite those specialists to the table to say, okay, because the solutions are probably already there, but many of us are not aware of it. So, Dr. Bettina, really. Okay.
Actually, I'm curious. Actually, I have a question for you. So we've heard that you have built a sandbox in the UAE to test a setup of new methodologies. And what I thought was really, so what I'm interested in is that because these things are so novel, we've never seen it, our ethics and our policies have to co-evolve with them. Could you explain a little bit more how you go about it and what your thoughts on this are? Is so we try new things, but it challenges our thinking. So do you have a process in place, how you evaluate and move forward? I'm just curious, sorry.
Certainly. I don't know if you are referring to the UAE human genome or not, but certainly, I mean, with anything that comes to the UAE, for example, it has to go through a regulator and also through the different ethical processes. These are the standard processes that goes through the ethical committee will evaluate if this is compatible with the UAE culture, with the UAE official religion, the Islam, and some of these things definitely will go through some discussion. For example, I'll give you a very simple example: DNR, or do not resuscitate, for a patient who is an advanced cancer. In the past, we used to resuscitate or do a CPR for every single patient. But through ongoing discussion, through the ethical committees, we started to open up. And more recently, in the last few years, we had an agreement that, we reached that, the conclusion that these patients do not have to go through a full CPR or life resuscitation. So every single decision in the country goes through a process, and certainly some things takes longer time. For example, even the donation of organs also has been going through lots of processes until it has been approved. So there are some challenges, but it goes through a series of processes to be approved, and certainly we're on the right track.
So you basically integrate your testing system into the normal process.
Of course, goes through the processes, and once it's approved, it goes to the direct clinical practices.
I wanted to reflect a bit on we talked about rare malignancies, but again, we are in an era where I would say we are oversimplifying cancer, if I can use that word. The reason is that we see a particular change and we categorize the cancer accordingly and we say, yes, we found this particular change and we're going to use this particular drug. In reality, cancer is much more complex than that. And as we start to evolve and learn, we're going to find that breast cancer, even though it's the most common malignancy, has so many subcategories that make every single category a rare malignancy. And if we don't collaborate on an international level, as we are gaining more and more knowledge in molecular and genomics and personalized medicine, we're going to be in a situation where we can't make decisions on are we making the right decisions for our patients because we don't have enough data to tell us that the outcomes are better. We might have general outcomes, but we won't have enough data to tell us in particular group of patients in that what now is considered a rare malignancy in breast cancer. I think we're heading there, but I also want to caution that an oversimplified view where we are right now, where we're jumping on the guns and we've been successful in certain cancers in having better outcomes, doesn't mean that every time we find a change, it's going to be that same success. We might need to find multiple changes to give you the summation of what this cancer is about. Again, we have to reflect back that this is a sample and it's a population. In that population, there are many other samples that we are missing out and we're generalizing and so on. So these things, we always have to remind ourselves that even though we're trying to find the solution, we shouldn't oversimplify and don't make it just about 1 + 1 = 2. It never is.
I think that will be our end note for this interesting discussion. And we definitely look forward to continuing that and remembering that the future is already here and it's really being shaped by the way we think and act today. So now I would like to hand over to my colleague Ingrid Heath. Ingrid, what's happening now?
Well, I have to ask you. Sorry, but do you want to do the Mentimeter question?
We've done it.
That's great.
Sorry, we're very efficient here on this panel. Well, we realized that the cost of genome sequencing is just a tiny aspect of it all. We have to take this holistic approach.
I did answer, and I did answer wrong. Sorry. Anyhow.
You wouldn't pay too much.
So, thank you so much for this, and it's time for a break then.
Great.
And we'll see you back here again at 4:30, so 4:30. And thank you.
Thank you very much, panel.
Hi everyone, my name is Carolina Klüft. I'm a former Swedish athlete in athletics. I was competing in heptathlon and long jump. But nowadays I'm retired from athletics and working with children's health in an organization called Generation PEP. It's a non-profit organization and I'm the operations manager, and we're working to try to make children move around more, be more physically active, and also eat better to have better food habits. And I'm very honored to be the one that will have this brain breaks with you. I know you have important days and a lot of important things to discuss, and I'm very happy to have these brain breaks with you where we'll move around a little bit to get up our energy in our body again, and to also activate our brains again after sitting still for a while. So please get up if you can. If you can't, you move what you're able to, of course. And I will start this first brain break with my first day in the heptathlon. And it's 4 events, and you don't have to be nervous now. You're not going to do the full event, of course, but we're going to do easy, small exercises according to the heptathlon. So I'll start with the first day, and the first event in the heptathlon is the hurdles, the 100-meter hurdles. So you will be standing up, and you will be moving the first leg right up, and the second one you will be moving out and forward. So first one and out with the other one. And you can also have your arms So be careful, so not kicking anyone beside you. Just stand here, moving. First leg, go up and down. Second goes out and forward. Great. Looks like we have some heptathlete talent in the room. Great, so the first event is finished. The second event is the high jump. So you will be standing just straight. You put down one foot and you go up with the knee and the arms. You want to go high, so go up and try to stretch yourself as good as you can. Up. Great. We do a few there. Come on. You look good. And we go up. And we go up. Great. And so the third event in the first day of the heptathlon is the shot put. So you will be standing with your legs a bit aside, and you will be holding your invisible shots put here, and your arms go up here. And then you go down with your knee and you push yourself out. And you push. So be careful now. Don't hit your friend. And push. Just a few seconds, a few minutes of a brain break will definitely be good for your health, both in the short term and in the long term. Well done. Okay, so the last event is the 200 meter running. So we will be running with our arms quite fast because now it's the 200. So try to move your arms quite fast. If you want to go with your legs, you can be standing a bit and running with small steps on your, just where you're standing, on your spot. And we're running 200 meter. Well, great job. Thank you so much for having this brain break with me, and I will see you again. Have a good day.